Hello. Thank you very much to the conveners and organizers for having me for this talk. So I'm Behrooz Ferdowsi. I'm a kind of a newish assistant professor in the Department of Civil and Environmental Engineering at the University of Houston, and I just started my lab about a year ago. So I wanted to just in a quick slide just say a little bit about my work. Okay, should press hard. No, it went too much forward. Sorry. Got right. So my research centers on friction and friction fluid coupling in granular materials. I am primarily interested, or until now, this has been primarily interested in behavior of soft materials, porous materials, because these systems are abundant on Earth's near surface. Many geological instabilities in short term and evolution of the Earth's surface and subsurface in kind of long term is controlled by the behavior of these materials. And more importantly, we actually, in many problems, we don't have good laws, good understanding, good mathematical relations, good understanding for the behavior of these systems, these granular and soft porous systems. Until nowadays, toward the end of my postdoc, I have primarily used computational models for describing or studying behavior of such systems, such granular and porous systems. More recently, now I have also an experimental lab primarily focused on rheology of this system, granular systems. And I am interested in behavior of granular systems across all their phases, from very dense to more dilute systems. Relevant to dilute systems, relevant to turbidity currents, dense systems relevant to landslides, and as such, and also across their fluid-driven and dry situation. And of course, these materials or the applications appear in landslides and mudslides, as well as in earthquake physics and glacier slides. So many of which are within the range of interest and topics of interest for the SZ4D. Right, it jumped again over a slide. Right, so kind of a canonical model for studying geological hazards, especially, or I would say frictional geological hazards, is earthquake problem, or nucleation of earthquakes. And in this case, if we want to actually describe or model nucleation of earthquakes using property of materials, the accurate model for that approach is known as frictional model of frictional sliding, in which relies on describing, relating the style of frictional sliding to actual property, especially frictional property of a localized shear zone, a fault gouge at the center of a tectonic system. And as Noah mentioned earlier, this model of frictional sliding is also relevant to other type of frictional sliding in the earth, such as landslides, as long as we can describe them or model them as a shear fracture or frictional fracture, and as well as to volcanic processes, such as here, the example is a caldera collapse or volcano caldera collapse. All these systems or part of these systems or these processes can be explained using the frictional model of a sliding. Right, and the other example of which I didn't have a slide for that, but the other example would be submarine landslides. So surface landslides, subaerial, as well as submarine landslides. They can, this model of frictional sliding could be useful for all these processes. So because of the interest to actually use this frictional model of a sliding, there has been, and the fact that we need material properties or constitutive relations for frictional behavior of materials to accurately model their behavior. There actually, in the past a few decades, there has been quite a lot of work on understanding, quite a lot of work, especially focused in the rock mechanics community, to understand how do transient friction and transient, frictional behavior of shear zones look like. And the classical case of those experiments is a fault shear zone or fault gouge confined between two plates under given confining pressure. And then we do in the laboratory, we do a number of experiments to explore their transient behavior. Obviously one of the popular experiments is known as velocity step experiments, in which I'm just showing one case of such tests. These are actual lab data. And in the lab, we usually for these systems, we see, okay, the pointer is dying almost. So for this system, we see when we take a rock sample to the lab and we put it under velocity step experiments, we see, looking for the alternative pointer. There was one. Oh, it's not here anymore. That's fine. So in those systems, we see in this system or in this transient protocol, we see a direct effect. This immediate change in frictional resistance of the system, followed by a gradual evolution of friction toward this new steady state. And you might have heard of the rate and state equations that are commonly used to describe such observations in the lab. And the idea of those rate and states are essentially constitutive equations for friction. And the idea of those is to describe this kind of empirical or lab observations using a two-part mathematical relation. One part describing so this is shear stress divided normal stress and sigma normal stress, and describing that this kind of frictional behavior in two parts, rate-dependent and a state-dependent part. The rate-dependent part of the rate and state friction is kind of figured out. But we know actually much less about the state dependent. There are various versions of mathematical relations known as internal variables, evolution of internal variables developed to try to come up with better state variables that describe actually what we see in the lab. I would say, I think the kind of consensus right now in the community is that a model of a state evolution known as a steep law is more successful in describing majority of lab data, not all of the laboratory observations for transient friction. But the caveat or the problem with the slip law version of the evolution equation for rate and state friction is that it doesn't have any physical justification. It's just a mathematical relation developed out of convenience and the fact that it describes lab data. So if we want to interpret or we want to upscale or relate material properties in the lab to geological field observation or observations in the field, actually relying on physical mathematical relation that doesn't have physical justification could be a little bit problematic. I should say that you see also here two coefficients of A and B. These are the range of A and B in most lab observations. There are about 0.1. Again, we don't have we don't have a full understanding of where they emerge from. These are observation based on lab data. So this is state of affairs, the fact that we have something that works, we have an evolution law that works, but we actually don't know why it works, and we don't have a physical justification for it. That motivated my interest in these questions and topics motivated my work in the past few years. During which I developed with my postdoc advisor, Alan Rubin at Princeton, I developed a very simple model of a fault zone using ideas from granular physics, essentially, looking or searching for an alternative mechanism that could give rise to transient behavior that we see in the lab, the rate and state-like behavior of shear zone. In this model, I'm basically having a layer of powdered or granular materials confined between two plates at a given confining pressure, and it works like a virtual laboratory as long as the physical laws at the contact scale are known. We can use it as a virtual laboratory to do all kind of experimental tests that we do in the laboratory. And using this model, I've been exploring behavior of this model in various loading protocols relevant to rate and state transient friction that we see in the lab. I should say that in this model, we have to assume some contact loss for the behavior of grains or granular materials. I'm assuming for normal contacts, grains interact with both in tangential contact as well as normal contacts. For normal contact of grains, I'm using a Hertzian contact law that's appropriate for spheres. elastic, as long as we believe, as long as we assume elasticity, that's Hertzian contact law is appropriate for behavior of spheres in normal contact. And I'm using a constant value of friction coefficient between grains. No time-dependent process involved here. So rate, when I say rate and state-dependent here, in this model, all of it should arise naturally from behavior of just bulk behavior of granular materials rather than any time dependency at the grain scale, at the contact scale. I should emphasize here, I'm using a particular version of contact law that's known as the Mendelin tangential contact. That's also standard classical for in these systems. And we have looked at a range of parameters in this system. Not, the exploration has been quite broad, but we didn't include everything that was possible. But I should emphasize that we looked at a range of damping coefficients. Then we noticed in these systems you have to damp them numerically, and we noticed that doesn't actually have an effect on the behavior of the system. So if I want to just talk about very briefly about the result that we have obtained in the last 2 years, was that, as I mentioned, I can take this model and do the kind of experiment we do in the lab. Here I'm showing an example of velocity step experiments. So friction signal versus a sliding distance for 1 to 4 orders of magnitude perturbations in a sliding velocity. So the important feature, or the important thing I should emphasize about this figure, about this result, is that if I take the friction signal and if I normalize that by the logarithm of velocity jump, all these signals collapse on this side. I'm showing it the downside. They're all collapse on a single, more or less collapse on a single line. And that's precisely what we see in the laboratory data. That's also prediction of a slip law version of the rate and state equation. So a simple granular model, and I should say, when we started doing this work, we haven't done any tuning of model parameters. We just used standard parameters of the model with the deformation, with the with the elastic, I should say, with the normal elastic property of quartz grains or glass beads, and we can use because the model follows closely version of this rate and state version, slip law version of the rate and state equations. We can use those equations and obtain rate and state parameters from this model too. And as I show here that the parameters are in the ballpark of what we see in the lab. I emphasize again, we haven't done any tuning of model parameters. So more detail about these results has been in our 2 papers we published in the past 2 years. And so this sounded quite exciting to us, the fact that the simple model can actually work. So I should briefly go over the results, but we actually looked at because the model worked quite well for describing transient behavior in velocity steps. We looked at the origin of rate dependence in this system, and we noticed, and so in rate and state equations, that rate dependence is known to arise from a thermally activated Arrhenius process. And we show here, and we can see that if I adopt that thermally activated process, the model results actually, that theoretical picture works for the granular model too. Here I'm showing the value of rate and state equation that we obtain for the granular model, and it's in the ballpark of lab data. This is obtained from energetic properties of the model. But that alone doesn't really answer the question of where this behavior is arising from, and is it also a general behavior of granular materials? So for that, we have to ask whether other type of contact laws would produce, what other type of contact law and material properties would produce similar observations, or what are the range of sensitivities of this model? And so I should this is part of our ongoing work. I don't want to show a lot of preliminary results here, but I can say that the actually version of contact law does affect the results. And it's actually an open question: what is the proper contact law following elasticity to include at the grain scale? That is, I think, is going to be a part of ongoing research. I hope to present more materials about that in an AGU poster in about a month. I also wanted to very briefly mention that. So we observed that in the model, the simple model works, produces many interesting behaviors within the lab, but it's a question: what is the actual granular materials in the lab? How do actual granular materials in the lab behave? And for that, I have been starting doing experiments. This is very preliminary data, but I started doing some very early experiments in the lab on granular materials especially at low confining pressures, to examine how generic is the transient friction rate and state-like behavior in granular materials. Do they emerge in all range of normal pressures, confining pressures, and velocities? And also to the degree that they actually, behavior in the lab actually looks like rate and state equations for the fault mechanics behavior. So that's so I should say these were results for quartz powder, quite fine grained materials. So I hope to do experiments for with more naturalistic materials in the near future to just look at those systems as well. So I want to thank you for your attention, and I also thank the funders. These are primarily funders of my postdoc work, and I'm happy to answer any questions.